Okay, well, I can't bring it in front of the camera and I don't want to lose the focus of the camera. Okay. But everybody here knows I've got a mass hanging from a string over a pulley. And that's attached to another pulley that's in a horizontal plane. And there's a beam attached to that pulley and it's going to rotate. Everybody knows that. We'll get a video of that up there somehow. So I just made a point flaw here. Just a little alignment issue. Okay. Now there's a 50-gram mass, 47 centimeters above the floor. So I asked, what's going to happen when I release things? What's going to happen energy-wise? And I got various answers. That came down to the potential energy is going to change, and that's going to create potential energy. Specifically, potential energy is going to decrease. Why is potential energy going to decrease? Because that suspended mass is positioned so that gravity gets to do work on it through that 47 centimeters. So gravity does positive work. What's the definition of change in potential energy? It's equal and opposite to the work done by the conservative force. Gravity is a conservative force. So there it is. Potential energy is going to decrease. Now, there's a little bit of friction in the system. It's pretty low friction. All the potential energy decrease, except a little bit, should go into some other form of energy. Okay. Well, it turns out that, friction does a little bit of work against the system, and that creates a little bit of heat. So some of the energy goes into heat. We're not going to try to quantify that. We'll take care of that in a couple of months. Okay. But the system's going to rotate, and the system has mass, so there's going to be motion of mass, and that's going to be kinetic energy, right? So we expect most of the potential energy to go into the kinetic energy of this system. Now there's a beam, and on each end of the beam, we've got 200 grams of magnets. Okay, the beam itself is 200 grams. So the question is going to come up. We have more kinetic energy in the mass of the beam, which is distributed from the center all the way to the ends, or in the magnets. We can determine that experimentally. If we just make a few assumptions, the main assumption being friction is pretty low. So what we're going to do, we're going to let this thing drop. We're going to do an approximate experiment because people didn't get me their data in time to incorporate it into today's class. Okay? So you're going to get to do it on your own. Now, and then report it next time. But it's very similar to what we're going to do here because I really want to know what's going on here. So then you should too, as I've said. You want to try to understand everything that's done in lab, quantitatively, qualitatively, conceptually, because 70% of the course is in the labs. Doesn't mean the lab is 70% of your grade. It means 70% of the content of the course can be seen directly in these labs. Okay. And what we're trying to develop right now is, incidentally, the concept of moment of inertia in rotational dynamics. Okay. You had some problems due today on rotational kinematics, which is something we've been talking about since the first day. Just what's rotational acceleration, the angular acceleration, angular velocity, how those things are related. It's exactly the same as it is for something moving along a straight line. The symbols are just different. And the meaning's a little different. Okay. The big thing, this moment of inertia thing, is going to be the analog to mass, though. Because you have different masses moving at different speeds. The energy goes into different masses differently. Okay, well, we have all that, but right now I'm just going to count this thing in my head, 1,001, 1,002, and you're going to count rotations. Okay? Because you can't see, where everybody's sitting, you can't see the descending mass that well, but I can focus on that, and you can focus on counting. Also, I'm not letting this thing descend the whole meter for two reasons. That's not two, that's two. For two reasons. One is that the thread almost becomes unwound if you go down a meter. If it only goes down about half that distance, then the thread's going to stay wound. It's going to be a lot less of a pain to work with this thing. Okay. Okay, so there it is. Well, let's just do it. I'm going to count, you're going to count. Okay, you determine how many rotations it went through and how much time. I'll determine how much time. Well, you determine how many rotations, I'll determine how much time, according to my count. And then I'm going to count a couple more rotations just to see how fast I think it's really going. Now, we could do this with timers and stuff like that, but it's going to be quicker if we just let me do it in my head, and we'll have some interesting errors that way. Okay. Okay, so here's a rough calculation. Here's a rough estimate of the numbers. I think they're actually fairly close. Went through about 20 radians from rest in 10 seconds. We assume uniform acceleration, even though the string was winding and it wasn't quite uniform, and there might have been some air resistance, but I don't think that would have been a big factor. Okay, but friction might not be consistent at different speeds, might not be constant. Might have some dependence in speed. Matter of fact, pretty sure it does. Okay, anyhow, roughly 20 radians from rest in 10 seconds. What do you determine from that? You determine that it averaged 2 radians per second. 20 radians in 10 seconds. You can visualize that. Okay. You don't need formulas to calculate that. Now, there are plenty of formulas, and you have to use them in many cases. In this case, you don't. Okay. So your omega average, angular velocity average is 2 radians per second. Final was 4 radians per second. Change was then 4 radians per second, right? Okay. Well, in this change, you could calculate angular acceleration. Just a change in angular velocity or a change in time. Okay. It's as simple as a change in just plain old straight line velocity with respect to time. There's nothing mysterious here. The mystery is in moment of inertia and torque and how all that works together. We're going to figure that out shortly. Okay. So that's not particularly relevant to what we want to do, because what we want to do is energy. Okay. Can you know one person? No, you can't at all. That says energy accounting. Look at it. Now you can read cursive. Okay. At least the words energy and accounting in my handwriting. Okay. Energy accounting. What's a change in potential energy? I said we had a mass, going to descend 47 centimeters. Did I tell you what the mass was? No? 50 grams. Okay. Well, let's just ballpark that as 50 centimeters and 50 grams. Okay. Just ballpark. It's going to be close enough because I'm counting in my head. I'm not even sure I was counting consistently. Okay. Although I got the same count from 2 different runs. Yeah. Okay. What's a change in potential energy? Well, it's negative of the work done by gravity. Work done by gravity is the weight times the distance. Okay, this is a force exerted by gravity, and this is the distance. Okay, distance parallel to the gravitational force, and that's positive. But the change in potential energy is equal and opposite to the work done by the conservative force. Okay. So this is negative the work done by the conservative force. Anybody got a result for that? Okay, you got a change in potential energy. See if you agree with my result. My results give me some pretty obnoxious inconsistencies. Okay, now change in kinetic energy of the magnets is 1/2 mv squared, where v is the velocity of the magnets, final velocity of the magnets. Magnets started at 0, they ended up at whatever the final speed was. So what was the final speed of the magnets, and what's the kinetic energy of those magnets? Tell you that there are 800 grams of magnets. Okay, wait a minute, 400 grams of magnets, I'm sorry. 400 grams of magnets on that thing, okay? I doubled twice. 400 grams of magnets. How fast were they moving? Okay, now people are trying to use a formula to figure out how fast this thing is. All I have to do is understand what a radian is. Okay, this thing's moving at about 4 radians per second, right? Well, the distance you move along the arc for each radian is equal to the radius of the circular path. Now, we'll assume the radius of the circular path is 30 centimeters. It isn't really, it'd be like 27.5 if you went to the center of the magnets, okay? But that even wouldn't be quite the right place, as we're going to see, okay? We'll just use 30. We'll just see how this comes out, and then you can do more refined calculations with all the data we have. And we can maybe learn what's going on with that beam, because the beam was common to every run of the experiment, with different numbers of magnets at different positions and so forth, okay? So the change in kinetic energy of the magnets, well, okay, 4 radians per second. That means the definition of radian says you move along the arc a distance equal to the radius, which is 30 centimeters for every radian. So that's going to be well, that's almost illegible even compare. But M is the mass of the 8 magnets at 50 grams apiece, maybe a little more than 50 grams, but just round things down and we can refine them later. Okay, so it's 0.4 kilograms and 4 radians per second at 30 centimeters for every radian is 120 centimeters per second, or 1.2 meters per second squared. Let me write it out again. It can be read. Okay. E squared 1.2, you get 1.44, half of that is 0.72. 0.72 times 0.4 is a little over 0.2. Okay. A little under 0.2. Wait a minute, no, so, okay. That's approximately to, I think, 0.29 joules. 288. Okay. Okay. So there's some energy accounting. Now, is there anything wrong with that? All right. Well, the problem here is somebody said, well, the final energy is not equal to the initial energy. Well, the initial potential energy, if you take the resting state as, you know, after the acceleration as your zero, your initial potential energy is about 0.25 joules. Your final kinetic energy is about 0.29 joules, but that's not all of it. There's also kinetic energy of the beam, and it's got 200 grams of mass. Okay, now it's distributed from the center out, so most of the mass is closer to the center than the edge. So it's not like having 200 grams out at the edge. Okay, you're going to get something a lot less. But we're already over the initial potential energy, right? Our kinetic energy gain is greater than our potential energy loss. Okay, now that could be due to the fact that I counted this thing in my head. Okay, and you observe the thing with your eyes. And even if you were running a timer, you can't completely trust your ability to time accurately. You could time it electronically. And we could actually attach an electronic device to that beam so we can get really precise information, okay? And we'll do that eventually. Here we got that beam is rotating on a sensor. It can be plugged into an interface. We don't want to use that right now. We want to get an idea. We want to get a more direct, tangible feel for the system than what we get just from the computer printout, okay? But then once we understand it, we'll get the computer printout and make minor observations. Okay, well, digressing a little bit. Okay. Okay. Kinetic energy gain is not going to exceed the potential energy loss, but that's significant. Uncertainties. Okay. Now, what would be interesting would be to get more accurate data, like the stuff that I haven't gotten from everybody yet, and compare the potential energy loss to the kinetic energy gain of the magnets. Okay. That could give us a clue as to how the kinetic energy of the beam is related to the rotational speed. but we're going to derive it now. We're going to see if the experiment results are consistent with moment of inertia. Okay, so I'm going to start with one thing. Okay. I'll just try to new board here. Not a level well, certainly matches this picture. That's okay. Okay, there we go. That's so good. I gotta be, you know. I can usually draw a decent circle. If I'm not trying to fit it to something else. That's not great. But now we got a beam. With the magnets. Mass is being total magnet mass M. Exert a force. I would just exert a force to one of the magnets. And I can easily demonstrate how that might be done. See? Just use another magnet. It's there. There it goes. Okay. So I just gave that thing some kinetic energy. It really wants to rotate this way. Why is it going to rotate this way so badly? Let's do that for another investigation. Okay. Pretty low.
I think the mass is still dropping. Yeah.
Okay, I know what happened. Yeah, we were, that was really dumb. Okay, I'm not even going to explain it. Okay, ready? So now we exert some force. Now, we're not going to use a magnet to move the thing. We're going to imagine some constant force. Just to make it easy. We could do the integration and all that stuff. That's fine if we knew what the magnet function was. But we're going to exert a force here. Force F stays perpendicular to the beam. Okay. And we'll do that through some angle delta theta. And this is a constant force. I say constant magnitude of F, but of course F itself is going to be changing direction as we move around. Imagine like you've got a little rocket engine on this thing, okay? And thing's burning at a constant rate. You've got a little fan on it. Fan's blowing air this way. You better balance it with another fan here and add the two forces, but that's okay. You've got some total force acting at the rim, at the radius r. And we'll let that be an r vector, okay? An angle delta theta, okay? It's a change in kinetic energy. Wasn't recording that, but we came out with the idea that, okay, the change in kinetic energy by the work energy theorem is equal to the work done by the net force. We have declared that this force is the net force. So it's force times displacement. The force is always perpendicular to the radial line, right? So it's always in the direction of motion. Okay, as long as the thing is moving in this direction, then you're going to have positive work. If the thing was rotating like this and this force is trying to stop it, you'd have negative work, which is good if you want to stop it. Okay, because you would decrease the kinetic energy. We won't worry about that right now. Okay, my question is, what's delta S? Okay. So we have this and F delta S. Well, delta S is just R delta theta. For every unit of angle, you move a distance equal to a radian along the arc. Well, it turns out that F net times the radius is the torque. Don't know if you're familiar with the concept of torque, but your book will tell you stuff about it. Okay, it's just cross product of R with F net. So if you got some weird radial vector out here in space with X, I, J, and K components, and some force with its I, J, and K components at whatever angle, you can do the cross product and get the torque. Okay, very simple to do that. And I won't expect you to totally understand how that works because you haven't had multivariable calculus, but that's the definition. Now, in this case, R is perpendicular to F net. So the cross product is just magnitude of R, magnitude of F net times the sine of theta. Theta is 90 degrees, sine of theta is 1, so you just get F net times R. Okay, and that's tau net. All right, there's your work energy theorem for torques and rotations. Okay, change in kinetic energy is that. Now let's get a handle on kinetic energy. We want the kinetic energy in terms of the quantities that we have here. Okay, so and we're talking about two magnets or whatever masses we've got on the ends here. So it's 1/2 mvs squared minus 1/2 mv naught squared, right? But those aren't angular quantities. Those are linear quantities. We can't use them here. So what's VF in terms of angular quantities? The angular quantity would be omega, right? How's VF related to omega F? Well, I'm going to tell you. It comes down to just the radian again. And be careless with that point for my square. Okay. I mean, VF is just R omega F, right? V is like how many meters per second. Omega is how many radians per second. And R is how many meters you move for each radian. If we simplify this, we get this. Okay, well, we can bring our thinking up to the top of the board here. One half M times R squared omega squared. Okay, digest that for a minute. Okay, somebody just made a quick comment. I made a change here. I have the square up here and the parenthesis here, and it was unclear where the square went relative to the parenthesis, okay? But if you look at what we've got here, it's clearly on omega naught, because it was on omega F, right? But the way I wrote it did confuse somebody, okay? Maybe more than one person. So I rewrote it to make it clear. It's up against the edge of the board. I've spent too much time there. So it wasn't as clear as it ought to be. You got our 1/2 mv squared for motion along a straight line. Okay. If we change the units to rotational units, we get 1/2 mr squared omega squared for kinetic energy. And it's very simple because V is just R times omega. So that's just 1/2 mv squared with V equal R omega, right? Let's make a little note here. So it's clearly kinetic energy. Of a mass M, distance R from rotating, distance R from the axis of rotation. We're going to get a loss from omega. This formula is the formula for angular kinetic energy. And if I equals mr squared, this is exactly the same thing as this. So this still is kinetic energy of that mass moving at that distance along that arc. Okay. E and my equals are melding together. Kinetic energy is 1/2 mv squared. I is the moment of inertia. Now I can come over here and pull on this string, which somehow unraveled, even though it wasn't, and the string itself has a weight that pulls it down. It'd be a tank. Okay, if I pull on this string, well, of course, the magnet being there, so if I pull on this string, I can feel the resistance due to the moment of inertia. If I try to stop this thing when it's rotating, well, the string unravels. Anyhow, I can feel the moment of inertia. Try to get the seat set up. So you can actually do that. Okay. Now, that's for two magnets at equal distance. Actually, for each magnet, you'd have half a big M if they're equal, right? Okay. So this one would have moment of inertia 1/2 big M R squared. And this would have moment of inertia 1/2 M big M R squared, right? Well, it doesn't take much of a jump. Understand? M1, M2, and M3 at R1, R2, R3. Each has its own moment of inertia. And there might be more masses. R squared. For the same reason, mass big M moving at angular velocity omega has kinetic energy it does. Okay. So your total moment of inertia is just this. And if you got more masses, you have them in. Okay. So for example, if I've got that beam here, and I set a magnet here and a magnet here and a magnet here and a magnet here, each of those magnets has a mass and a distance from the axis of rotation. So it's got a moment of inertia that you get from that mass and distance from the axis of rotation. You just do mass times just square that distance. At angular velocity omega, kinetic energies are kinetic energy at first is I1 omega squared Total kinetic energy is this. We look at total moment of inertia is this. Well, total kinetic energy, whatever kinetic energy that system has, it's going to be the sum of all the kinetic energies, right? Well, each of these terms has a 1/2, and each of these terms has an omega. So kinetic energy total is just this. Okay. And of course, the I total is the sum of all these I's here. So if we want to know how the system is going to interact with the torque, well, go ahead and work. This thing, done with it. Think about this one a minute. Torque is R cross F net or tau net delta theta. No, sorry, torque is R cross F net. In this case, it's just R times whatever force we're exerting, okay? And the change in kinetic energies is tau net times delta theta. So your change in kinetic energy is this. That's the work done by the net force. Okay. And that's equal to the change in your kinetic energy, which we write this way. It's going to turn out that the angular acceleration is equal to, well, let's do it this way. And that is I alpha. Now, there's a direct correlation between what we have here and what we have for uniformly accelerated motion along a straight line, for any motion along a straight line. So we're going to just go back to linear kinetic energy, rotational kinetic energy. Do you understand? Go back over if necessary, see what your book tells you. Because it's going to be pretty much the same thing, okay? That's exactly the same thing this is. That just comes down to the fact that omega, that V is omega R. You take that R squared you get when you square omega and combine it with the mass and you get your moment of inertia, okay? So you got this. You have okay, that force is mass times acceleration or linear motion. It's I alpha. Tau net equals I alpha. Net torque equals I alpha for rotational motion. Okay. For the beam, the tension in the string was producing a force on the pulley, which made the thing rotate. Okay. That was a torque. Torques make things rotate. You notice that on this side, every place you've got an M, on this side, you've got an I. I'm trying to push a heavy mass, even on a frictionless surface, I've got to exert a lot of force to accelerate it. If I'm trying to accelerate a rotational system, it's the rotational resistance, the moment of inertia. It causes me to have to exert more torque to get the same acceleration on an object with greater moment of inertia. You calculate the moment of inertia of this system, except you don't know how to calculate the beam. And there's an et cetera here. In your book, I believe, has a table that shows you all the correlations. But if you understand these two, that's the key. Do your best to understand these rather than just pulling out formulas to try to solve problems. Okay. Although if you do pull out a formula to solve a problem, then think about how that's related to this whole development. Think about why that works. Don't just be content to get an answer. Because if that's all you know how to do, you're not going to perform as well on a test. You're not going to end up as good an engineer. You're not going to understand the physics well. You might do well enough in a course to get through the physics course. You get through with a better grade if you understand it. You're a really good formula jockey, yeah, you can fake it. That's okay. But I kind of want to advocate that you really think about what things mean. What's going on? Not just what formula do I use? What's going on here? Okay. I knew what I was going to do next, and then I digressed. Let me stop and think for a second. Yeah, I was going to talk about the moment of inertia of that system. Okay, what can you tell me about the moment of inertia of this system? Where's a mass that's at some distance from the axis that you can get your hands on? Well, one of the magnets, right? Okay. Now we're treating this mass as a point mass at a distance of 30 centimeters. We'd be better off to treat it as a point mass at a distance of 27.5 centimeters. And I'm going to make the calculation easy, right? And we can always modify. Okay, so I equals mr squared. That's easy. It's 0.05 kilograms times 0.3 meters, 0.015 square of the meter. Okay. In other words, think about what you're doing like I don't. Okay. That's 0.09. 0.09 times 0.05 is 0.0045 kilogram meter squared. Make sense? Now, what we've currently got on that system that you can see there is 8 magnets. Okay. I think that comes out 0.036 kilogram meter squared. Again, don't trust my calculations. What we don't know is how to calculate what you don't know. It's how to calculate the moment of inertia of that beam. This we can derive easily with a simple integral that breaks the rod down into increments, just like you do with a Riemann sum. It is a Riemann sum. Okay. We're not going to prove anything theoretical. We're just going to use it till I take it to a limit. We're going to get a very simple interval. And it is a very simple interval. Okay. Now we're going to do that next time, so you have something to look forward to. But I can tell you what it is. It's 1/12. The mass is 0.2 kilograms. Length is 0.6 meters. Squared. Well, I keep forgetting to square that. That's 0.036 multiplied by 0.2 is 0.0072 kilogram meter squared. Let me check that. It's 0.12. I've got too many zeros in there. And then this equals 0.06 kilogram meter squared. Okay, so you've got this, the magnets, and this, the beam itself. And I'm a little leery of that because I have to think that the magnets have a total mass that's equal to the mass of the beam. And that mass is all out at the edges. So the magnets have to have greater moment of inertia than the beam. Magnets are equivalent to taking the whole mass of the beam and making a big clump of it and putting it out at the end with some invisible but rigid rod. Okay. And something's wrong with I just don't see it. Anyhow. Four radians per second. Kinetic energy for the magnets is 1/2 times the moment of inertia of the magnets, which is this. Eight times 36. Is 0.288 joules. That's a quantity that we've seen. Remember? When I had the 0.29 joules. Said that was a 0.288. So if I've done that calculation correctly, and this kind of confirms it, that agrees with the kinetic energy we got from the magnets. Okay. The moment of inertia here had one too few zeros in it. Okay. Now, what's this moment of inertia in comparison with this? Well, this is 1/6 of this, isn't it? It's like 6 into 36. Okay, so only 1/6 of the kinetic energy was in the beam itself. Roughly. Again, the magnets were a little closer on the average. Their masses were a little closer on the squared average. And we'll talk about that next time, okay? That threw that off by just a little bit. Everybody's looking at the clock. Okay. And I'm kind of looking at it too, because I'm gonna let you out of here in time. So this all works pretty well. It turns out that we have about 1/6 of this would be about 0.05, so about 0.33 joules of kinetic energy in the whole system at 4 radians per second. Okay. And that exceeds 0.5 joules that we got from the decrease in kinetic energy. Okay. To the 0.25 joules. So we got to kind of reconcile that, but that's all just experimental error. Okay. So if we get more precise data, and if you get me your data, do this analysis. It's just find the moment of inertia. And see if you got more kinetic energy than you lost in potential energy. Okay. Just that simple. And that's the simplicity of the work energy theorem. Okay.